Hello, good evening. Is my sound clear? Anyone can confirm with Interact?
Hello, yeah, it's clear.
Perfect. So good evening, everyone, and welcome. On behalf of IEEE MBS eJust Student Branch Chapter, in collaboration with IEEE Sensors Council Egypt Chapter, it's my pleasure to welcome you all to today's session of PRISO Research Program 2026 webinar series. Thank you all for joining us this evening. Whether you are a student, a researcher, or a professional interested in sensors, electronics, and biomedical engineering, we are glad to have you here. Today's session is titled From Defects to Diagnostics, PANI-Based Organic Sensors, Bridging OFET, Degradation, and Glucose Biosensing. We will be exploring the connection between organic semiconductor devices, sensor degradation mechanisms, and how these insights are driving advances in glucose biosensing for next generation biomedical applications. And to guide us through this topic, we are truly honored and welcome our speaker, Dr. Sameh Abdellatif. Dr. Abdellatif is an associate professor of electrical engineering at the British University in Egypt, co-founder of the Fab Lab at the Center of Emerging Learning Technology, and secretary of IEEE Sensors Council Egypt chapter. His research spans semiconductor devices, organic electronics, nanostructures, and sensors technologies. With a portfolio of over 160 scientific publications and more than 25 research grants, he was also recognized among world's top 2% most influential researchers in the 2025 Stanford University Global List. With that, I will hand it over to Dr. Abdellatif. The floor is yours. Welcome and thank you for being with us today.
Thank you very much, Mr. Abdul Rahman. I hope that you can hear my voice well.
Yeah, your voice is clear.
Yeah, thank you very much. So let me first of all thank IEEE eJust Student Branch. Of course, my acknowledgement is extended to my colleagues in IEEE Sensor Council Egypt chapter. And I wish that during the 35 to 40 minutes, I can provide something that makes benefit for you. So now let me please start sharing my screen, and I wish it works fine with you. Okay, so I started my screen. I just need if you can confirm that you can now see my slides. Okay, that's great. Okay, thank you very much. As I mentioned, I'm expecting to have this talk within 35 to 40 minutes. I will call it an intermediate talk in terms of technicality. So we will try to explore some what we can call advanced topics in the field of biosensors. However, I call it intermediate, not an advanced talk, because I choose to make this exploration for the advanced topics somehow in a horizontal way rather than in a vertical way. So I will not going to dig into a detailed description of every and each advanced topic we are going to tackle. Rather than I will try to show a series of advanced topics through our recent publication, either in IEEE journals or other journals. Maybe it come across that one of these topics seems to be interesting for you. So in the beginning of the presentation, just give me a very few minutes, maybe 1 or 2 minutes, to describe quickly who we are. We are a group in the British University in Egypt, in the Faculty of Engineering, under the name of Electronic Fab Lab. And what are our research philosophy? Our basic research philosophy is based on what we can call multi-scale model. What I mean by multi-scale model, when we consider a device, we attempt to consider this device starting from what we call an atomistic level up to application level. Here we have 3 main stages. The first is what we can say that this is the material level in terms of a material selection, characterization, sensitizing, fabrication. Mostly we are considering thin film structures. Then segmenting these thin films together, we construct a device. Then we try to enroll this device in a form of a certain application. We try that we do this cycle or this process in two parallel ways: a fabrication way and a simulation way. Maybe in terms of simulation, definitely there is some challenges, but I think you will agree with me that the main challenges comes for the fabrication. Herein, we choose, or actually, let me be more honest and say that we were forced to be far from those devices that require clean room fabrication facilities, because we don't have clean room fabrication facilities. That's why in the next 35 to 40 minutes, I don't think that you are going to hear the word silicon, for example, simply because we don't have the capability to synthesize, to process, and to fabricate, and to process silicon in the standard CMOS or in the standard VLSI technology. That's why our devices is a bit far from silicon. Usually we call this wet chemistry processing, or sometimes they call it in the literature homemade devices. We need a controlled environment, but we don't need a clean room facilities. In the previous 4 or 5 years, maybe just before the COVID era, in the late 2019 exactly, we started a new phase in our process, which is integrating artificial intelligence. And we start to think how we can integrate, how we can integrate artificial intelligence in our devices. Maybe earlier than us, maybe in 2014, 15, some groups start to introduce a term called material informatics. And you can search or you can Google this term. The term material informatics was mainly related to how we can use informatics, machine learning, deep learning, and so on, in terms of material selection and material optimization. And we scale up this term to what we can call devices, electronic devices informatics. And we start to integrate AI, mainly I will consider here machine learning and deep learning, into electronic devices. The process of integration can be considered from different scenarios. From the scenario of optimization of the device, from the scenario of predicting the time-dependent performance of the device, and the scenario of fault detection and diagnostic analysis, which we will try to consider in this presentation. Our focus area is mainly toward three main devices. Energy harvesting devices, which is the core of our group. We mainly work with perovskites and decent-sized solar cell. Maybe I think 50-60% of our publication in this direction. We have some attempts in energy level, which is somehow high level. I mean here, system level energy integration, mainly solar cells again. And our topic for today, which is biosensors. So most of our, I think, let me say 100% of our publications are considered within these three areas, maybe with a bias toward the energy harvesting, mainly light harvesting devices. So this is simply what is Fab Lab, what we are doing. And let's now jump into the core or the main topic of today. I will try, actually, I don't have a lot of information about the type of the audience, so I will try to start somehow from scratch with a quick procedure in order to engage most of you to our discussion today. So basically, let's just start with a very simple and a very basic question, which is what is the definition of a sensor? And I think most of us during our undergraduate studies somehow consider or tackle this question, a definition for a sensor. And when we return back to old radical measurement and instrumentation books, you can find a very standard definition about sensor, considering that sensors are those devices that convert physical changes into output signals. What do you mean by physical changes? Actually, everything. this physical change. It can be an environmental change in temperature, humidity, carbon dioxide, oxygen, whatever. It can be a biomarker. It can be a pressure. It can be a force, whatever it is. And what we mean by output signal, in the basic definition, it was one out of four very traditional signals. Variation in voltage, which is definitely the most famous, variation in current, variation in resistance, or variation in capacitance. Like, for example, when we deal with piezocapacitive sensors or piezoresistive. Later on, this definition starts to be expanded a bit. And here we can say that the term output signal means any sort of signal that can be processed. And I will use this expanded definition later on when we consider optical biosensors, for example. Because in optical biosensors, we don't have an electrical signal, we have an optical signal, which is, for example, optical transmission or optical reflection, and still we consider here now this as a signal that can be processed later on. When we first introduce the term sensors, what we can have or what we can think about is these discrete sensors you usually use or you usually apply in your life. For example, you can open your mobile phone and open Amazon app and start to order a temperature sensor or a humidity sensor, and you can have this nice small digital sensor where you have a plastic packed device with a temperature sensor, an LCD, and there is some sort of a small embedded system in between. It measures the temperature and it displays the measured temperature. These types of sensors, what we can call discrete sensors. It's something like when we consider discrete electronics, when you go to RAM and buy your resistance and capacitors and a breadboard and connect these together and form a circuit using discrete electronics. However, when we go more and more toward technology, we start to introduce new terms in the literature. And here we have, in the last maybe 25, 30 years, we have two new terms when we consider sensors. The first one is the term smart sensing. And when we mean here the term smart is that it's no longer a device, a sensor with a display. No, we have the term wireless sensor network, where we have nodes are connected together wirelessly, either through RF or Wi-Fi or internet connection, sort of internet connection, pushing or gathering data into a central hub. And I can, using my mobile phone or my laptop, I can demonstrate the temperature in 1,000 node in the same screen, and I can process this data. And this is extremely useful when we consider IoT, for example, Internet of Things, or IoT Square, Internet of Tiny Things, or IIoT, Industrial Internet of Things. Then another term starts to appear in literature, which is self-powered sensors. And what do we mean by self-powered sensor? That when we consider a normal sensing node, we can say that the weakest point on this sensing node in terms of lifetime is the battery. Usually we have a battery with 3,000, 4,000, 5,000 cycles. And once the battery is expired, you have to dispose of this node and you have to get a new node and so on. What if we have an energy harvesting device that either fully replace the battery, which is somehow an optimistic scenario, or at least boost the lifetime, expand the lifetime of the device? So now we have, instead of having only a battery, we have an energy harvester, and then we have a power management circuit that combines power and starts to drive power to the node and so on. That's why we have the term self-powered smart sensors. Moving again toward the developing of sensors, we start to have another term, which is the SoC. I think maybe most of you hear about it, which sensor on a chip. So instead of using these discrete electronics in order to form our smart node, now we can integrate our sensor in the IC, in the chip itself. And here, it's about minimal area, minimal power consumption, portability, and a lot of advantage. For example, if you check your iPhone or your Android phone and you think about how many sensors are in this phone, and you think what if these sensors are all about discrete sensors, then you need something like maybe 100 times the volume of the mobile to occupy all these sensors. But you have all these sensors in a very small device simply because you have the capability to integrate many sensors in very small area using the SoC or the sensing on chip technology. And as I think all of you know, the main key player in the chip technology is a transistor. So the question here maybe is how we can use our famous MOSFET or our famous transistor to be a sensing device. And this may be the first part of our discussion, which is how we can use the OFET, and here the word OFET stands for organic field effect transistor, how we can use OFET to be a sensing device. Then we can integrate it in what we can call SoC or sensing on a chip technology. In the second part of the presentation, we will consider another type of sensors, which is SPR or surface plasma resonance. Honestly, it's not 50-50% discussion. It will be more biased toward the left side. So we will consider more about OFET and less about SPRs. So let's now go to the first part, which is how we can use transistors. I will kick out the letter O a bit, so I will keep it more generic in terms of fit. And definitely, as far as you study electronics, computer engineering, computer science, mechatronics, you hear the term FET before, the field effect transistors, which is the most famous family of transistor ever, and the key building unit in any electronic devices, either analog or digital. We know the most famous member in this family, I think you will agree with me, is the MOSFET, the metal oxide semiconductor field effect transistor. And when you start to think about the MOSFET, maybe the first or the easiest way to describe a MOSFET is it's a three-terminal device where we have a controlling element, which is the gate, and we have two connections, which is the source and the drain. So first of all, in order to push water to flow, here what I mean by water, of course, is between quotation current. In order to push water to flow, you have to give some sort of force between quotation voltage to your controlling element, which is the gate. This minimum voltage required to make water to flow is called the threshold voltage. Then the more force you apply to the controlling element, which is the gate, the more water to flow, which is the current. So whenever you open the controller, whenever you have more and more current flowing in the tube, as you can see, you reach a point at which you reach the maximum flow. So if you start to rotate the controller more, you will not get more water. You will not get more current. So simply, when we describe MOSFET operation, we say that we have three regions of operation. We have the cutoff region, no water, no current. Then we have what's called the triode region. The higher the voltage applied to the gate, the higher the current flow in a linear relation between the VDS and the ID. And finally, we have the saturation region. Again, the question is, can you use this MOSFET to be a sensing device? The issue is any sensing device needs what we can call an interfacing area. If you just recognize a diabetic patient when he starts to measure the glucose level in the blood, he or she, of course, make a 1 or 2 drop of his or her blood on a surface. This is what we call the interfacing area. The interfacing area is the area at which the physical phenomena we are going to measure interface with our device. The main concern when we consider MOSFET is an isolated device. We don't have the accessibility to have this interfacing area because simply source and drain are covered by electrodes. The channel in between is covered with the oxide of the gate oxide and the gate electrode. So there is no accessibility to insert or to have this interfacing area. Here, we return back to the root of the family. We have to remember that the MOSFET is just a one member out of many in the family of the FET, the field effect transistors. We have other members as well. Three of these other members are related simply to the arrangement of the source and drain and the gate. So simply, we have source and drain and gate. Then we have full combination. We can insert the source in the top, the source and drain in the top, and the gate in the top as well, which is simply our famous member, the MOSFET. But we can also put the source and the drain in the top while the gate is in the bottom. Here it we call bottom gate top contact. We can put everything in the bottom, which we call it bottom gate bottom contact, and so on. Maybe your question is, what is the advantage of making bottom gate top contact or making bottom gate bottom contact, for example? My answer now will be the interfacing area. So I'm not sure if you can see my mouse, but the figure A here, in figure A, you can see that when I insert the gate in the bottom, the space between the source and the drain, which we call it theoretically the channel, is now an open space, an open interface. So I can inject here any sort of interruption to my device. So I can use it as a sensing area. Same apply here when I consider a bottom gate, bottom contact. This interfacing area is open to interact with the semiconductor. So in this case, when I shuffle the configuration, I start to make or generate or create what we can call an interfacing area. Now, what is my target? My target is that when an interruption happens, an interruption here, I mean an intersection between the physical phenomena to be measured and the material, this interruption makes some sort of a change in the material property. And this process, we call it in the biosensing technology, the immobilization. We have a biomarker, which is lactate, glucose, whatever it is, and we have a semiconductor material. Once this process happens, that the biomarker interacts with the semiconductor material, this interaction should result in a variation in the property of the material. And this variation in the property of the material will then be transferred to an output signal in a variation of voltage or current or resistance or capacitance. Okay, so what if this blue active layer of a semiconductor we are using in the device is one of what we call an organic semiconductor material? Here we can return back the letter O. So once the active layer of the material, of the device, is an organic semiconductor, we can call it an OFET device, or organic field effect transistor. And again, the selection, the material selection process is based on the capability that this material can interact with a certain biomarker to transfer the physical variation or the biomedical variation in this biomarker into a variation in current or voltage. That if you just recognize the flow, you will find that we consider here two main parameters. First, the selection of the architecture, the configuration. We choose either bottom gate, bottom contact, or bottom gate, top contact to generate the interfacing layer. Then the material selection, which select a material which will interact with a certain biomarker. For our work, we are using two famous organic semiconductor materials. We have a better experience with polyaniline, which is abbreviated by PANI here. We call it polyaniline has more than different formats. So mostly we use nanofibers, polyaniline nanofibers. And also we have a recent publication with pentacene as well. But for polyaniline, we choose polyaniline. Again, if you return back to our history as a group, you will maybe guess the answer that we are using polyaniline because we can synthesize and we can deposit polyaniline as a thin film. Because again, this is the key word whenever we choose a material, that we have the capability to synthesize and to fabricate and to turn it into thin film. Polyaniline has an advantage of interacting with different biomarkers. Personally, in our group, we use it in two different types of, actually, yes, let me say now two different types of sensors. The first one for lactate measurement, and the second one is for a caudal protein, a famous caudal protein called troponin. Troponin is a protein that starts to increase whenever or something like an alert for a heart disease. So it's a bad sign to have higher troponin protein in the blood. And as you can see here in the left-hand side, here we start to make different biomarker doses. And once the biomarker increase, there is a variation in the current. So now here, as you can guess from the y-axis of the left-hand side graph, that's the indicator here. The output signal here is the current. So we can call this between quotation a current sensor. And this is the story beyond. So now, from a transistor point of view, you fix everything. The gate voltage is fixed. The drain source voltage is fixed. So simply from our knowledge in semiconductors, then we should have a fixed operating point on the IV curve. However, due to the immobilization of the troponin with the organic semiconductor, which is the nanofiber polyaniline in our case, this affects the conductivity of the layer, and you can expect that it's negatively affect the conductivity, because the higher the troponin concentration, the lower the drain current. So everything is fixed in terms of biasing, in terms of voltage biasing, but the operating point is moving or is varying due to the variation of the conductivity of the channel or the semiconductor due to the immobilization process between the polyaniline and the biomarker, which is troponin in our case. You can find in our publication maybe 5-6 papers in this track, and maybe also 2-3 papers about lactate, mostly in IEEE transaction nanotechnology. And you can find, as I mentioned earlier, you will find some console simulations based on for these devices, as well as, of course, experimental testing for these devices. But it's not only about using polyaniline in the OFET configuration. Polyaniline has also advantages to be used in other sensing phenomena. So I will jump. Okay, I'm sorry. Before I jump, I missed one slide about the performance, performance evaluation, or the evaluation performance of these devices, which is very interesting, by the way, because when you consider this device, you can consider this device from 2 points of view. You can consider this device as a transistor, OFET is a transistor. So you have the capability to evaluate this device as a transistor. Whenever you are evaluating transistor, there are famous performance parameters to evaluate transistor, like the threshold voltage, the on-off current ratio, the subthreshold swing, the mobility in the active region or the tried region, the mobility in the saturation region. So you can consider it from this point of view. And again, you can also consider it from a sensing point of view. If you consider it as a sensor, so we have also another set of parameters that can evaluate sensors. For example, or the most famous one is the sensitivity. And basically, the definition of the sensitivity is the variation in the output signal, which is here the current, with respect to an incremental variation of the input indicator, which is, for example, troponin or lactate or whatever. So a very interesting study you can see when you are trying to link everything together. For example, how can we correlate the threshold voltage with the sensitivity? Or to make it more easy, we can think about how we can correlate the threshold voltage with the power, because again, power is very important. If you remember my early slides, we say that the battery management system, or what we call the BMS, is a critical point of design in our sensing node. Whenever you seek to elongate the lifetime of the node, one of the main aspects is to make some sort of power management for your electronics in order to consume the minimum power and energy possible, so that you can elongate the lifetime of the node. So when you have a sensing element with a microwatt power budget, much better than a milliwatt, and nanowatt is much and much better. So if I generate a transistor with a threshold voltage 0.1 volt, for me, this is more beneficial than having a transistor with 1 voltage threshold voltage. That's why you will find in literature the word ultra low threshold voltage. Because whenever you are implementing a sensor, you are seeking a minimum operating voltage, a minimum biasing, which will typically equivalent to a minimum power consumption. Again, this is another parameter. We also, it's not only about sensitivity and power, it's also about limit of detection, which is the minimum value, the minimum biomarker value you can measure. This is called the LOD, or the limit of detection. So you can start to think about all these parameters, either from a transistor level point of view or from a sensor level point of view. And then you can correlate this, as you can see in the graph here on the left-hand side, you can correlate this with the material parameter. When you have a material, you have a material selection. So I can use polyaniline, I can use pentacene, I can use another organic semiconductor. Okay, I am going to use polyaniline. Then I have, as you can see here, the thickness. I have the doping. Again, in the OFET, it's not only about the semiconductor material. We also have a gate oxide or a gate insulator, an electrical material in the gate, which has a K index. So we have to think about it. We also have the oxide thickness, which is a critical parameter in the OFET device. So the process of optimization here is somehow a sophisticated process of optimizing all these parameters. And as you can definitely agree with me, I assume that you will agree with me that no free lunch. It's about a trade-off. You can never reach a point where everything is good. It's about what is your priority. I'm seeking for a very high sensitive troponin device, then maybe you will somehow expand the power budget. Or in the other hand, I'm seeking for a very low power device. Maybe I can now be a bit flexible about the sensitivity or LOD or other parameters. Okay, as I mentioned, it's not only about measuring measuring troponin and lactate. Polyaniline also can be used in measuring other biomarkers. One of these famous biomarkers is glucose. Polyaniline, still we are using nanofibers of polyaniline, can be used as a working electrode in glucose sensors. Here you can find our paper in IEEE Journal of Sensors, where we optimize polyaniline for the use of a glucose detection. And you can see here, these are the samples. It goes a bit from gray to green after the insertion in glucose. And this is the transfer characteristic curve when you have glucose concentration on the x-axis, and still this is a current sensor, so we can have current in the y-axis, and you can, from this graph, you can estimate the sensitivity of the device, which is simply the slope, and the limit of detection, which is the intersection with the x-axis for this graph. Okay, we start our discussion with the term SoC, or sensor on a chip, but it's not only now about SoC. We have now another interesting device, which is OOC, or organ on a chip. Organ on a chip, relatively, it's a new technology. The main factor for market penetration for OOC is coming from pharmacology, from drug testing. When you read here, or when you read in this topic, you will find that people who are working in creating or in recipeing medicines, they are facing a very critical problem related to testing, drug testing. The problem is the most commonly used way to test drugs is using animals. This is one of the most famous. Of course, I'm not expert in this, so I'm just transferring what I read. And using animals have two main challenges. The first is time. You need big time. That's why the cycle of medicine generation is relatively slow. The second is the capability to mimic the impacts on animal to the impacts in human. It's not only, it's not always one-to-one. The capability now, which is, by the way, clinically approved now, to have organ on a chip is a massive step in drug testing. Now, expect that you can have a hardware, an AI accelerator, GPU, with organ on a chip, and you can have something like a data for 1 million patients. And this is realistically, by the way. And you test the effect of the 1 million patient in one run. So instead of making 1 million sample, 1 million real sample on animal, using one chip, you can squeeze the time on using organ on a chip. So capability of making organ on a chip and using it as in drug testing is extremely of a potential use. And now if you go to literature, you will find that we have heart on a chip, we have lung on a chip, pancreas on a chip, and definitely the key word here is sensors, because all of our organs are working using our human sensors. So whenever you think about an organ on a chip, you think about sensors and controllers with, of course, a lot of sophisticated electronics. We have a recent publication in Q1 journal, which is Advanced Devices and Instrumentation, considering heart on a chip and lung on a chip. Maybe you can access it if you are interested in this topic. Another key or new trendy topic in this field is what we call brain-computer interface, or PCI. Those who study computer science or computer engineering are familiar with the term HCI, human-computer interface. But now in electronics, in microelectronics, we have the term BCI, or brain-computer interface. In this term, we have different subdomains like brain penetrating microelectronics and brain surface electronics. But simply the idea is how to embed a microelectronic chip in the brain so that this microelectronic chip collects the signals coming from the brain and send it to an outside actuator to act accordingly. So simply, now I have my mouse in point number A. I just need to think about that. I need to move this mouse from point number A to point number B. I just need to think. Once I think about it, this signal will be transferred to my laptop, and my laptop will move automatically the mouse from point A and point B. Again, this is not some sort of a science fiction. This is already clinically tested, and you will find a lot of research where we have this EEG signals or LFP signals captured from the brain and transferred into outsider devices. And again, here organ in a chip play a very important role, because you can simply mimic the brain with a chip, and you can make a full demonstration for the prototype. Okay, now let me move to the second part of the talk. As I mentioned, it's not 50-50, so please don't feel in sort of that you don't feel boring, because we just need maybe 10 minutes to finish, which related to biosensors. And in optical biosensors, it's a story about no longer we have electrical signal, we now have optical signal, we have some sort of laser beams, and we are modulating these radar beams in order to make a detection for different biomarkers. Optical biosensors is an extremely huge area with maybe something like 9-10 sub branches. I will just go with one of these branches, which is SPR, or surface plasma resonance. Maybe you hear before about the word plasma or plasmonic effect, which is related to the resonance effect due to the free electron in a metal. So whenever we have a plasmonic effect, we have to have a conducting material. In our recent publication here, we have a very recent publication in optoelectronic letters, Springer Nature, considering SPRs in what we call HIV DNA detection. We use two different configurations for this implementation. The first one on the left is a prism. It's a simple diffraction prism with graphene. And the one on the right, we call it photonic crystal fiber. The term photonic crystal is mainly related to what we call refractive index contrast. So in order to make a photonic crystal structure, you have to have a combination or a contrast between two materials with different refractive index. The higher the gap between these two refractive index, the higher the photonic crystal effect. Again, it's a different area, which is totally optical, but the same concept applies. If you remember my early slide, when I considered the OFET, I told you that it's first about selecting the architecture, second about selecting the material. So here's the same. First, we select the architecture. Either we are going to prism or optical fiber, photonic crystal fiber, PCF, and under the PCF we have different configuration, D shape, B shape, C shape, and so on. And once you select here the configuration, you go now to the materials. So for photonic crystal, for example, we have two different materials, a conducting material and an insulating material. And we have an analyte where the biomarker will flow. And here you can do a lot of optimization process in order to select the combination between different materials, seeking for SPR resonance or surface plasmon resonance. And as I mentioned earlier, the output signal here is an optical signal in terms of optical transmission. Okay, maybe the last topic to be discussed here, which is, from my point of view, is the most interesting topic for me, how we can use AI in these devices. How we can use AI in order to enhance our understanding to these devices. And as I told you earlier, we asked ourselves this question 7 years ago, maybe. And after 7 years, I can say from our point of view, which is definitely very, very limited, we can use AI in 3 different directions. 2 of them, I call it under the word of forward production, and 1 of them under what we can call backward diagnostics. Let's start with the forward. The first one is optimizing the devices. As you can see, either in the OFET or even in the SPR, you have a huge amount of what we can call design parameters or adjust tuning parameters. Definitely, we have powerful simulation tools. Whenever you are using any sort of a numerical model, either using finite element method or finite difference time domain or any sort of numerical solver, these are very powerful tools. That's true. However, whenever it comes to have something like 9, 10, 11, 12, and so on, designing parameter, it becomes very, very challenging to use numerical solvers. And these need a very high performance computers with a huge amount of time. Herein, creating databases with few samples and using machine learning and deep learning can definitely facilitate the process. So optimization is the first track. The second is how we can measure our device performance in terms of time, the time dependence of our device performance. Whenever you send a paper to any sort of a journal, definitely one of the reviewers will ask you about, okay, this is a good device, but what about the lifetime? How can I guarantee the lifetime? How can I guarantee the repeatability, which is a very critical factor, especially when you are doing or when you are fabricating device not in an autonomous way. As I mentioned earlier, we are using wet chemistry. So if I go to the lab and I fabricate 10 devices, definitely I will get 10 results. Definitely I will have variation. Anyone who studied chemistry will agree. So it's another parameter. Again, and also the control of the fabrication process, the control in the thickness, the control in the doping, the control on the deposition of the electrodes, all this stuff. These all data insert uncertainties to your measurements. How you can correlate all these variations to the live performance, the reliability and the repeatability and the sustainability of your device. Here, again, machine learning can play a very good role. Personally, I use maybe something like 21 algorithms in studying our devices. From my perspective, this is actually maybe not to be taken as a fact, but this is at least my point of view. For optimization, we usually use random forest, and for data production, we use LSTM, long short-term memory. Again, this is just an output based on our data set, but it can differ from one to another. The third track, which is, we call it the backward diagnostic track, is relating to how we can first recognize, second, diagnose our faults. As I mentioned earlier, definitely you will have faults. You will have samples which showed performance, not a standard performance after fabrication. But it's not about to go to put these samples into rubbish. No, you have to study why these samples are between quotation fault, what we call in machine learning the fault patterns. And then after recognizing this fault pattern, you have to classify the type of faults. And here classification models in machine learning can play a good role. So relating or converting the data coming from your results and trying to investigate the reason of each fault is another interesting point to be studied. We have a recent, we have a publication, a paper which is still under review in Journal of Material Science in Electronics in this OFET performance and how we can diagnose the OFET performance based on the fault patterns. And we classify different sources of fault and how we can classify the type of the fault based on the output measurement characterization of the device. So again, this is another place where you can integrate AI for your electronic devices. As I mentioned earlier, we have to agree that what I'm saying to you is a very limited vision. Definitely, there are a lot of other tracks where you can integrate AI in order to more and more study your electronic devices. By the end of the day, we can say that we have 4 stages, as I mentioned earlier. First, it's about architecture selection. how to select the appropriate architecture, appropriate configuration for your device. Second, it's about material selection. Third, it's about AI integration. And finally, clinical testing. So the key words for the talk was first, the microelectronic architecture, or the microarchitecture in general, because we have optical as well. Second is the material, and the interface is a key point when we turn our transistor from MOSFET to bottom gate, bottom contact, or bottom gate, top contact to generate an interface. And finally, it's about using artificial intelligence in order to optimize and enhance the understanding of our devices. That's all from my side. You can find this talk in my YouTube channel. This is my YouTube channel. You can find this talk in my YouTube channel. I think the talk will be also available in our colleagues in IEEE eJust student branch, and I think it will be also available in the IEEE Sensor Council Egypt chapter YouTube channel. So please feel free to rewatch it again if you think it deserves. Finally, I maybe use this nice platform to announce for a coming event. The British University in Egypt, with a collaboration with the IEEE Sensor Council and the IEEE Sensor Council Egypt chapter, is going to make a 2 days workshop with main keyword dealing with digital twin in biosensing application, or digital twin application in biosensing. Digital twin is as interesting topic as biosensors as well. Actually, I was thinking about inserting something about digital twin in this slide, but I think it will take more time than allowed. I already exceed the time, I think. So I don't have the gap to insert more about digital twin. The event will be in 2 days. The first day will be lecturing. We will have international speakers who will come physically to Egypt to give us 1 day about biosensors and digital twin. And the second day will be mainly hands-on with real biosensors and embedded systems. So far, we didn't start to call for registration. Of course, this is a fully free workshop. I think in a very short time, inshallah, we are going to call for application. Just you can follow the social media of the IEEE Sensor Council Egypt chapter, and you will find a call about the application for registration. Maybe the only drawback that it will be a very limited seats, because in the hands-on, it will be 100% working on lab. And as you can understand, whenever it comes to work in a lab, we have to have a restricted number. But I hope that it will be an interesting event for you, and I encourage you, as far as you're interested in biosensors, to apply for registration. Again, that's all from my side. Thank you very much. You can find here my email, and this is a QR code for my Google Scholar, and definitely feel free to email me if I can technically help in anything. And I think now that's all from my side, and maybe I can return to my colleague in IEEE eJust if there is any question. Thank you very much.
Thank you, Dr. Sameh, for this insightful presentation. We really appreciate you taking the time to share your ideas with us today. Thanks again. Is there anyone have a question to Dr. Sameh? Okay.
Can I proceed?
Yeah, for sure.
Yeah.
Okay.
First of all, thank you for this lecture, Professor. Very clear presentation. I have 2 questions. My first question, so for the immobilization process in the OFET biosensor, so does the biomarker directly interacts with the material? Doesn't usually interacts with the specific kind of medium that's on top of the interface layer? For example, since I'm from the biomedical background, take antibodies, for example, fixed within the material to get some kind of reaction with the actual biomarker, you want to measure, glucose or protein, or you meant the biomarker is directly interacts with the material. Yeah.
Should I go answer or wait till the second question?
No, go answer for the first question.
Okay, thank you. Okay, 100%. You are totally right, and I am totally wrong. Actually, I just need to be a bit shallow, and I didn't go into details, but you are totally right. In order to make the interaction, or what we call the immobilization between the biomarker, which is troponin, for example, lactate, and the polyaniline, we have to have an antibody. Totally, you are right. I'm just trying to make it as simple as possible because I'm assuming that we have audience from different backgrounds, and I prefer not to go into biomedical details about antibodies and so on. But you are totally right.
Okay, thank you. So, and my second question is it already shown, like in the literature, that there is a measurable pattern that AI can actually predict from parameters like material type or the architecture? And what if actually the results are actually correlated to outside variables like the fabrication method, or variables you did not consider, like the number of defects in material, or I don't know, like any other variable? Yeah.
Maybe I didn't get your question 100%. You mean to what extent the fabrication parameter impact the sensing sensitivity, for example, and limit of detection and so on?
Yeah. For example, if you're going to try to predict a specific architecture, LOD, or sensitivity, some like variables, like for, let's take, yes, fabrication methods, like are they taken into account? Like
okay, so when you use the term predict here, you mean that when I'm trying to use AI for this purpose, that's right?
Yeah. Yes.
Okay, I got your question. Okay, this is a very, very interesting question. Thank you very much. Here is the main difference between using simulations and using AI. When you are using a simulation tool, it's about hypothetical, theoretical environment. So you have to act to integrate this, what we can call abnormal effects, like, for example, the defects in the material, as you mentioned, the variation in the thickness, the morphological variation of the layer, because simply you don't have a clear flat layer, it's impossible. All these impacts, you have to integrate it in your simulation model. In AI, you don't need to do so. Why? Because you see the AI with experimental data set. As far as you see the AI with an experimental data set, this data set itself includes the uncertainties. So you don't need to embed the uncertainties.
Okay, I understand now. Yeah, okay, thank you very much.
Thank you.
Okay, it's great. Thank you again, Dr. Sameh, for this insightful sessions. And now we can end up this session.
Thank you very much.